Okay, here we go. 4-3. This is part 3, the third and last part of like graphing functions. That's why this guy's here. Analyzing functions. It's not much different than what we were doing before. Like if we're trying to locate increasing, decreasing, maxes, and mins, what do we do for that?
First derivative.
First derivative. Okay. If we are trying to do concave up, concave down, or POI, that is the second derivative, okay? That all still applies. The only other issue is now they're gonna throw in
No, we're not throwing in anything.
vase, which I think we maybe have already addressed, okay? Now they're gonna throw vase into the mix, and
Is
vase,
that like the third derivative or something?
no. Vase are going to be another critical number. And that's all that it does. Okay, so we're going to be doing the same process again, but we're going to have to be conscious of where the vase are located, okay? Because there's going to be critical numbers there as well, all right? So that's the only difference in here, all right? So in many problems, the properties of interest in the graph or the function are symmetries. So we can have x-axis symmetry, we can have y-axis symmetry, we can have origin symmetry. X-intercepts. How do you find x-intercepts? By the way, how do you find x-intercepts?
Good question.
You plug in 0 for x.
0 for y.
Oh yeah.
X-intercepts plug 0 in for y. What does it mean when it says relative extrema?
Max and min.
Maxes and mins. Okay. Intervals of increasing, decreasing. That's the first derivative again, so I'm going to do this. Okay. Asymptotes. So we have vase and Haas. Do you remember how to find vase?
Nope.
Bottom equal.
Yep, denominator equal to 0. How do you find a Ha?
The weird thing. The rules.
N and M. Okay, I'm not going to write the rules out, but that's what you look at is N and M, the degrees of the numerator and denominator. Periodicity, we don't really do a whole lot with periodicity, but that's going to be like with sine and cosine functions. Like they have a period of like where it stops and starts and then it like cycles again. So it's like a repeating pattern of a graph. Okay, how do you find y-intercepts?
Setting for 0 and for what x.
0 for x.
Yeah.
Concavity and inflection points, that's your second derivative. And then behavior as x goes to infinity or as x goes to negative infinity, this is like your end behavior. Which we also talk about in terms of limits. So a lot of times we'll say the limit as x goes to infinity, or the limit as x goes to negative infinity. What is happening to the graph? So end behavior or limits.
So what did you say?
Periodicity, like for example, like you don't have to write this down, but the graph of like sine, like if I'm graphing y equals sine of x, you don't know this yet, but you will here shortly. In trig, the graph of sine looks like that.
Yeah.
But then it continues on forever, left and right. So he goes like this, and he continues to go like that. So this chunk from here to here, this is just one period.
Okay.
Right? So like a graph, if we take that period, it's like copying and pasting him. Periodicity is gonna like just represent multiple periods of the graph. Okay? Make sense? Good? So all of that stuff we kind of have gone over and know how to do, or should, possibly. And let's do this one. So here's my function. Find him. It says identify the locations of the intercepts. So we need an x-intercept and we need a y-intercept. Okay, that's this part. Relative extrema, what's that mean?
Max and min.
Max and min. Okay, inflection points, so POI, S behind it. I'm going to put an S behind mins and maxes because maybe there's more than one. And then asymptotes, so we need a va and we need a ha. And maybe we'll have more than one, I don't know. Okay, so
Let's solve for y.
Let's do max and min, that's your first derivative. And your poi is gonna be your second derivative.
Yep.
So maybe let's do all of the things that don't require derivative first.
So like x is
Should we do
less.
that?
So we can plug in 0 for x.
Okay, so if we're doing x-intercept, we wanna plug 0 for y, right?
Yeah.
Yeah? Okay, so let's do x-intercept first. So I'm gonna plug 0 in for y, so 0 equals all that junk. 2x squared minus 8
I thought.
all over x squared minus 16. Cool.
Add the 8 and the 16.
Pull apart the bottom.
I don't wanna do that.
Oh yeah.
I want to.
I wanna do that. I wanna solve for x. Make the bottom go
Multiply.
away. If you multiply the bottom over,
He's gone.
anything times 0
Down.
is 0, and he's gone. So 0 equals 2x squared minus 8. Now what?
Add 8 divided by 2. to
Add the 8 over.
square root.
So I have 8 equals 2x squared. Divide by 2, so that is
4
4 equals x squared. And take the square root.
equals 2.
X equals
Plus
plus minus 2. Plus minus 2. So we have 2x intercepts. Plus minus 2. Alright. Now, I already gave you the answer. X-intercept plus minus 2. So we have right now, this is the graph. I gave you the graph. I gave you the answer. We have plus minus 2, which is this dot right here and this dot right here. So that's what we have so far. Yeah? Okay. Finding the y-intercept. How do we do that?
Plug y in for x.
That's easy.
Plug 0 in for x.
What
Yeah?
did I say?
Plug y in for x. I don't know. So y equals 2 times 0 squared minus 8. You can do this in your head if you don't want to write it all out. So this goes away. 2 times 0 squared on the bottom. We have negative 8 over negative 16, which is positive 1 half. Positive 1 half is this little dot right here. So that's my y-intercept. 1 half. Okay? So from the graph, that's all we know is those 3 dots. Got it? All right, let's do va and ha. How do you find a va?
You
So denominator
do the
equal to
bottom.
0.
Denominator equal to 0. Okay. So if my denominator is x squared minus 16, I'm going to set him equal to 0. Then what?
Add 16.
Add 16. X squared equals 16. Then
X equals plus minus
4.
4 plus minus 4. So I have 2 vas at plus minus 4. Great. So here is one va at positive 4. Here's another va at negative 4. Cool.
2
Oh.
over 2.
'Kay.
Hot is 2.
Okay, ha's, we do n and m. So n is the degree of the numerator, which is 2. M is the degree of the denominator, which is also 2. So then
2 over 1.
I look at 2 over 1, which is 2. So my ha, y equals 2, and that's where this dotted line comes into play. Got it? Nice.
Now we cry.
And now we cry. And now we be very sad. Alright. How shall we? We gotta do the first derivative. Alright, how shall we take our first derivative? What would you like to do?
Cry.
Shall we do the quotient rule?
No.
Y prime equals. Alright, do you remember the quotient rule?
F prime.
If you don't want to write down the quotient rule, just follow me up here and you help me.
Prime
Okay? If you don't want to write this down, just follow me up here.
over G.
F prime G minus G prime F all over G squared. Okay. So what's F prime gonna be?
F prime.
Oh, this is gonna be kind of nice actually.
It's gonna be 4x.
4x is F prime. G is all x squared minus 16. Minus, what's G prime?
G prime is 2x.
2x. And F is the entire top. Okay, the bottom is G squared. So x squared minus 16 squared. Bruh. Okay. So, first derivative. Alright, let's distribute the 4x through. 4x cubed minus, what's 4x times 16? 64? 64x? Okay. And then negative 2x goes together. So that would be minus 4x cubed. Oh, baby. Do you see what just happened? Plus 16x. all over x squared minus 16 squared. Do you see what just happened?
X cubed. No.
4x cubed minus 4x cubed. Really? Seriously? Cool. Minus, what's negative 64 plus 16? 48.
question.
48. Is it 48?
Sure.
Negative
Good job.
48x?
Hey,
Oh,
we
we
can't
can't
see you.
see.
What happened? Ah! No. Oh, I don't know why he's doing that. I'm still going, right? Am I still going?
Strange.
There we go. Can you see now?
Sure.
Alright,
So the 4x.
Negative 48.
4x.
all over, or
It's
negative
gone
48x,
again.
No puts there.
x squared minus 16 squared. That is what?
F prime. Or no.
Y prime or f prime of x, whatever. That's my first derivative. Okay, now what do we do with that?